Hey everyone, I apologize I can't be there in school today, but hopefully this video will help guide you through a few of these problems so that you can feel comfortable doing the one for homework on your own. So for starters, I noticed that this packet does not have a title, so I titled it Net Change or the Definite Integral. We talked about integrals last week, whether we saw each other on Thursday or Friday. And that had to do with finding area under the curve, right? And now we're looking at specifically between two x values, how to find the area under the curve. So this first problem says the population of a tiny island country changes over time as people immigrate and emigrate. Suppose f of t gives the rate of change of the population, where t is measured in years. So what we're looking at in this graph is a rate. And the way that I describe it to people is that if you integrate the rate, what you get is the accumulation of that rate. So in this case, we're integrating people per year. So we're getting an accumulation of people. We're figuring out what that total number of people is. And I know we've talked about this in class before, but I just wanted to repeat myself to make that clear of what we're doing. So A says use a right-hand sum with 3 rectangles to estimate the net change in population between 1 and 7. Well, we know how to do that. We need to find our delta x first. So that's b minus a, 7 minus 1, divided by the number of rectangles, which is 3. That gives us 6 divided by 3, or our delta x is equal to 2. Now for a right rectangle, we're going from 1 to 7. So from 1, we know that with a width of 2, that takes us to 3. So a right rectangle is going to be the height at 3. And then going from 3 to 5, the right rectangle is the height at 5. You'll notice that's negative. That will come into play in our answer. And I'm going to highlight this as well. And then from 5 to 7, again, a right rectangle takes us up to this point here. And what we're finding is all of this area right here. So that area is going to estimate the area under the curve. Obviously, it's not going to be super accurate, but you know, it gets more accurate as we have narrower and narrower rectangles. But just as a reminder, we're finding the net change in the population. That's equal to 2 times 8, because our width is 2, our height is 8 for that first rectangle, plus it's going to be 2 times negative 16. Our width is 2, and our height is negative 16 right there. And then we have 2 times 48. So plus 2 times 48. Add that up, that gives you 80 people. So in this tiny island nation, from time t equals 1 to t equals 7, we're saying that the net change, they added 80 people. They added 80 people. If that was negative, that would mean that that's how many people left. So between years 1 and 2, the population increased by 80 people. That's what that means. It says, how would you visualize the exact net change in population? Well, we would find the exact area under the curve from t equals 1 to t equals 7. And what does that look like? Well, we call that the definite integral. That's the definite integral. And that is shown by the integration symbol that we talked about last week. I'm going to draw this down here. That's our integration symbol. We're going from 1 to 7 of f of t dt. Okay, so f of t is the thing that we are integrating. That's this function in this graph. And we're integrating from 1 to 7, finding that area from 1 to 7. It says, was the population larger at time t equals 1 or at t equals 7? Well, think about this for a second. We know that from 1 to 7, we added 80 people. So at t equals 7, it's going to be larger, right? And it's going to be larger because our net change was positive. Positive 80 people. All right, and this says, suppose the population at time t equals 2 was 2,000 people. Write an expression involving a definite integral which gives the number of people at t equals 4. So this is saying write the exact number of people. So at t equals 4, the population was equal to, we started with 2,000 people, and then we added the accumulation of this rate. So at t equals 2, we had 2,000 people. So started with 2,000 people, we're going from 2 to 4 of f of t dt. So our 2,000 is the initial population at t equals 2. All of this represents the net change in population from t equals 2 to t equals 4. Okay, so hopefully that's clear that would give you the exact answer, right? This represents the exact answer. Obviously, we don't know how to do that just yet, of how to find that exact answer whenever it's a curve like this. But on the next problem, we have a similar problem, but now we have straight lines. And the nice thing is we can find the area underneath straight lines using triangles or trapezoids or rectangles, squares, etc. Just a reminder, the area of a trapezoid, I think I wrote this on your homework page, but just to remind you, B1 plus B2 divided by 2 times the height. All right, so we'll remember that in case we need to use that later. I don't know if we need it for this problem or not, but anyway, it's there. So this says the function r of t, again a rate, graph to the left gives the rate at which water is flowing into or out of a backyard swimming pool. Time t is measured in hours, and the rate r of t is measured in gallons per hour. So if you integrate gallons per hour, you are finding the accumulation of gallons. At time t equals 0, there are 700 gallons in the pool. We're going to remember this, that we're starting off with 700 gallons in our pool. This says, write a definite integral that represents the net change in the amount of water in the pool from 0 to 6 hours and find this net change exactly. All right, so this first problem, again, to find the net change, we're doing a definite integral from 0 to 6 of r of t dt. We always write the smaller number on the bottom of the integral, the 0, and the larger number or the 1 to the right on top. So 0 to 6 r of t dt, that is equal to, we're trying to find the area underneath this curve from 0 to 6. Looks like we have a rectangle here, so that's going to be 120 times 5, plus we have a trapezoid right here. That's, I said B1 plus B2, so let's see, 120 plus 90 divided by 2 times h. H is the distance between them. In this case, the distance between them is just 1. All right, when we add these together, we get 600 plus 105, and that gives us a total of 705 gallons that were added from 0 to 6. Let's take a look at letter B. B says, how much water is in the pool at time t equals 6? Well, we just said that we added 700 gallons. All we need is to know how much we started with, and that brings us back up here, right? We started with 700 gallons. So this is just 700 plus what we added, the net change, 705, and we're left with 1,405 gallons. Part C says, when is water entering the pool at the greatest rate? Well, remember, we're looking at the graph of rate. So we're just looking at the highest output. The highest output is going to be the greatest rate, and that highest output occurs right here. So when is it entering the pool at the greatest rate? It's entering from do this in a different color just to stay color-coded, I guess. From t equals 0 to t equals 6. You could write this in like bracket form. You could write this as an inequality. I know not a lot of students like doing that, but you could write this in however method that you want in order to get your point across. So from t equals 0 to 6, and what is the greatest rate? Well, it's just the output. It's 120 gallons per minute. I'm sorry, not gallons per minute. Gallons per hour is our unit. My bad. 120 gallons per minute would be insane. All right, so 120 gallons per hour is our greatest rate. This says, when is the amount of the pool in the when is the amount of the water in the pool the greatest, and at what time? How much water? At that time, how much water is in the pool? I'm trying to go a little too fast here. Let me slow down. So when is the amount of water in the pool the greatest? Well, it's going to be the greatest when we're switching from water going into the pool to water going out. So let's think. Water's going into the pool at a positive rate here. It's still going in at a positive rate because all of these outputs are positive, right? Positive, positive, positive. At time t equals 9, we switch from a positive rate to a negative rate, which means that water is going into the pool here, and here water's going out of the pool. So, therefore, we know that that's the time when we have the most water in the pool. So at t equals 9, when water starts to flow out of the pool. I know it didn't ask for why, but I'm going to write that just so that we know why that is. All right, it says, at that time, how much water is in the pool? Well, we know that this area here is equal to 600. We found that in part A. We just need to know what's this area here and add that onto the 600 and then the 700 that's already in the pool. So we have, let's see, 700 plus 600 plus that area here is just a rectangle, so 1/2 times 4 times 120. 4? Yeah, 4. 1/2 times 4 times 120. Apologize, I am unprepared for this. How much? I need to bust out my calculator. This is 2 times 120 plus 600 plus 700. All right, I did this really quickly on my phone. I got 1,540 gallons. Double check that just to make sure, but I'm pretty sure that that's right. So that's how much water is in the pool at time t equals 9. All right, this says, between 4 and 12, what is the net change in the amount of water in the pool? Express your answer as a definite integral. All right, between 4 and 12, what is the net change? So net change is just, we're just talking about the integral, right? The area under the curve from 4 to 12. So integral from 4 to 12 of r of t dt. Again, we're integrating the rate to find the accumulation. So from 4 to 12, let's see, this area here is going to be 120 times 1. So 120 times 1 is just 120. Plus, we said that next area is, let's see, 1/2 times 4 times 120, which is 240. So 240 is this area right here. That's the area of a triangle. 1/2 times 4 times 120. Minus, it's going to be minus because area underneath the curve is going to be negative. So we're going all the way to 12 here. So we're going to subtract off that area because that represents water flowing out of the pool. So that is minus 1/2 times 3 times 90, 1/2 base times height, 1/2 times 3 times 90. If you add all of that up, you should get 225 gallons. Notice it's not asking how much water is in the pool, just what the net change is. Okay, so we're not worried about that initial 700 at that point. F says, recall that at time t equals 0, the pool contains 700 gallons of water. Is there ever another time t at which the pool contains 700 gallons of water? If so, approximate t on the graph. Well, we know that at t equals 9, we're up to 1,540 gallons. So we've added 540 gallons, right? Because 1,540 minus 700 gives us 840 gallons. So the question is, do we ever lose 840 gallons? Well, let's take a look at our graph up here. Here, this area here is 1/2 times 6 times 180. Let's see, what's that give us? That's 3 times 180. 3 times 180, that's 540. Okay, so at time t equals 15, we lost 540 gallons. Okay, we lost 540 gallons, which means when are we going to lose 300 more, right? Because we have 840 minus 540 gives us 300 gallons. All right, I would love for you to pause this video and try this one on your own. Hopefully you've been doing that throughout this video, kind of pausing and comparing your answers to mine. But what we want to know is where in this area are we going to hit 300 gallons, right? Because we still need to lose 300 more gallons to get back to the 700 gallons of water. We know that we're losing it at a constant rate of 180, right? So basically we're asking 180 times how many hours is going to give us 300 gallons that we've lost. Well, this is easy math. We just divide by 180. And we should get x equal to 1.67 hours. Okay, so that means 1.67 hours after time t equals 15, we've lost 300 gallons. So therefore, at t equals 16.67, because 15 plus 1.67, we lost 840 gallons. So there is our answer right there. All right, almost at the end here. This says, let W of t be the amount of water in the pool at time t. Sketch a rough graph of W of t and make sure that your graph agrees with your answers to the previous parts of this problem. Okay, so your graph, again, rough sketch. Rough sketch. We know that at the beginning, we're at 700. We know that we max out at 1540, so that's going to be like up here. We know that that happens at 9, so let's say that this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So at 9, we're at 1,540. At 0, we're at 700. That is going to look, well, I guess looking at this graph, this is our derivative graph, and we know that this is going to be increasing everywhere from 0 to 9, and from 5 to 9, it's going to be concave down because the derivative of that is negative. So from 0 to 5, it's a straight line. And then right around 5, this switches to concave down. I know that doesn't look super concave down, but this section in here should be somewhat concave down. And then it continues to be concave down until 15. And we know that at 16.75, we are back to 700 gallons. So let's see, that was 9, 10, 11, 12, 13, 14, 15, 16, 17. So this was 9. This is 17. So somewhere around here, we're back at 700. And it's concave down until 15 when it goes linear. All right, so linear between 16.75 and 15, and then we go concave down. All right, so something like that. And obviously this is going to keep decreasing as time goes on. All right, finally, last problem. It says put the following quantities in increasing order. Okay, so we know, let's see, we have 5 to 8, 5 to 9, 5 to 10, and 5 to 11. Well, we know that the biggest is going to be 5 to 9 because that's the biggest positive area. So I think we can safely put that one at the end. The integral of 5 to 9 of r of t dt. All right, if we look at 5 to 8 and 5 to 10, I'm going to erase this. 5 to 8 is this area, and 5 to 10 includes this area. Well, this positive blue cancels with this negative 2. So actually, this negative blue. So actually, the 5 to 8 is the same as the 5 to 10. So we can say that this is greater than the integral from 5 to 8 of r of t dt, which is equal to the integral of 5 to 10 of r of t dt. And let's see, 5 to 11, 11 keeps going negative, so that's definitely going to be the smallest one of all, right? Because we're taking away even more gallons. Then we subtract that area out. And this is then greater than the integral from 5 to 11 of r of t dt. Okay. Hopefully this helps to guide you through your homework, which should also be handed out to you. Do your best on it. We will talk about anything that you're confused on when I am back, which will hopefully be on Thursday or Friday, depending on what period you have. All right. Hope this was okay. Good luck with your homework, and I will see you all later this week.